So we want to do kind of a summary of our transformations that we've been playing with in Desmos so we get a better idea of how these work. And we're going to work with the function f of x is the square root of 1 minus x squared. Something to notice, if we create a table for x and f of x, when x is negative 1, I get the square root of 1 minus negative 1 quantity squared, which is the square root of 1 minus 1, or the square root of 0. So I get 0. So for just f of x, when x is negative 1, I get 0. When x is 0, I get the square root of 1 minus 0 squared, or just 1. And when x is 1, I get the square root of 1 minus 1 squared, which is 0. And it turns out that the graph is negative 1, 0, 0, 1, 1, 0 is a semicircle. And so that's the original function f of x. And now we're going to talk about transformations of this function. So the first transformation we're going to talk about are transformations that are translations and shifts, so they don't actually change the shape of the graph, which you've seen some of these in Desmos. So we'll start with g of x equals f of x plus 2. We want to see this algebraically first of all. So g of x is the function f of x, or the square root of 1 minus x squared, and then you add 2. So before, when x was negative 1, I got 0. Now I'm going to get 0 plus 2, or 2, as my output when x is negative 1. When x is 0, instead of 1, I get 1 plus 2, or 3. There's 3. And when x is 1, I get 0 plus 2, or 2. And so my transformed graph for g of x is the same as the graph of f of x, only now I can see that my whole entire graph hasn't changed shape, it's just shifted up vertically by 2. Now something similar happens when I look at g of x is f of x minus 2. So now, instead of outputting, when x is negative 1, instead of outputting 0, I output 0 minus 2, or negative 2. When x is 0, instead of outputting 1, I output 1 minus 2, or negative 1. And when x is 1, instead of outputting 0, I output 0 minus 2, which is minus 2. And so you can see this is the same graph, same shape, shifted down by 2. All of my outputs have shifted. And we say these two transformations affect the outputs, and so they're a vertical transformation. Now let's look at what happens if instead I look at a g of x where I do something to the inputs. So instead of adding 2 to the outputs, I add 2 to the input first. So let's talk about what that looks like algebraically. Algebraically, g of x, which was the our f of x was the square root of 1 minus x squared. Now instead of putting my input x in, I put in x plus 2 and I square that. So in the end, algebraically, this transformed function equation looks like the square root of 1 minus x plus 2 quantity squared. So it's a little bit more work to kind of think about what's going to happen with my function. I could try x is negative 1. When I do negative 1 plus 2, I get 1, and then f of 1, if you recall, was originally 0. So that's one way to think of it. So when x is negative 1, I still get 0. But if I plug in x equals 0, x plus 2 is 2, and if I try to plug in 2 into g, I see that I get, I still plug in 0 into g, but when I plug in 0, I get the square root of 1 minus 2 squared. So I get an imaginary number, a negative 3 under the square root. So I need to pick inputs that actually give me real number outputs to be able to graph this on a real number graph. So I'm going to pick inputs. Let me cross out. I'm going to pick the inputs that I wanted originally. So before we did negative 1, 0, and 1. So I know that those output 0, 1, and 0. So the question is, what x values correspond so that when I add 2, I get negative 1, or when I add 2, I get 0, or when I add 2, I get 1. So the x value that I can add 2 to get negative 1 is negative 3. The x value I can add 2 to get 0 is negative 2. And as we've already seen, the x value I can add 2 to get 1 is negative 1. So in some sense, what just happened was all of my x values shifted to the left by 2 for the same outputs. So let's graph that. At negative 3, I get 0. At negative 2, I get 1. And now we can see on the graph that my function has shifted to the left by 2. So I applied a transformation, notice, to the inputs. This happened inside my function. So this was something that affected the inputs. And it gave me a horizontal transformation. Something similar is going to happen with f of x minus 2, only now what I would try is, maybe you would imagine probably it's going to shift to the right by 2, and you would be correct. If I input 1, 2, and 3 in, then g of x is the square root of 1 minus x minus 2 squared. So when I plug in 1, I get the square root of 1 minus 2 squared, which is 1 minus 1, or 0. And when I take the square root of 0, I still get 0. When I plug in 2, I get the square root of 1 minus 2 minus 2 squared, or 1 minus 0. The square root of 1 is 1, so I still get 1. When I plug in 3, I get the square root of 1 minus 3 minus 2 squared, which is 1 minus 1 squared, so I get 0 again. And you can see that all of my outputs have shifted to the right by 2. Again, I affected the inputs, and so that moved my graph horizontally. Something to notice is that when I add 2 to the outputs, I shift up. When I subtract 2 to the outputs, I shift down. But when I add 2 to the inputs, I shift left. And when I subtract 2 from the inputs, I shift right. And my corresponding equations you can see here. To get those horizontal shifts to the left or to the right. So now let's look at stretching or shrinking a function. So we'll start by transforming the outputs again. So I'm multiplying the output by 2 here, and let's talk through what happens. So g of x is going to be 2 times the square root of 1 minus x squared. And so when I inputted 1 before I got 0, 2 times 0 is still 0, so I'll still get 0. When I inputted 0 before I got 1, but 2 times 1 is now 2, so now my output is 2. And then when I input 1, I get 0, 2 times 0 is still 0, so I still get 0. And notice I get this stretch. So 2 times f of x is we would call this a vertical stretch away from the x-axis and in this case it was by a factor of 2, so my outputs kind of doubled away from the x-axis. If instead I multiplied by a half, when I input -1, well, first of all, let me write down the equation. G of x is going to be 1/2 the square root of 1 minus x squared. When I input -1, I'll get a 0 under the square root, so 1/2 times 0 is still 0. When I input 0, I'll get a 1 under the square root. 1/2 times 1 is now 1/2. When I input 1, I get a 0 under the square root, and 1/2 times 0 is still 0. So we get 0, 1/2, 0 for the inputs of -1, 1, and 1, or -1, 0, and 1. And you see that I have a vertical shrink towards the x-axis. Again, you notice these transformations are affecting the outputs, f of x, and they are vertical transformations. Now let's look at stretches and dilations that affect the inputs. So I'm going to want to use my inputs -1, 0, and 1 into f, but that means my interesting inputs into g, so g of x is the square root of 1 minus the quantity 2x squared. So the values of x that I need to put into g to get the same outputs that I had for f are actually negative 1/2, because then 2 times negative 1/2 is negative 1, 0, and then 1/2, because again, then 2 times 1/2 would be 1. And so when I plug in 1/2 for x into g, then when I multiply it by 2, I'll get negative 1. When I square it, I'll get 1. Then I'll do 1 minus 1 and get 0 under the square root and get 0 like I did before with f of x. But now that's happening when x is negative 1/2. When I plug in 0 for x, I still get 1. When I plug in 1/2 for x, again, I plug in 1/2 into x, I multiply that by 2, I get 1. When I square that 1, I get 1. 1 minus 1 is 0, so then I get 0. So something interesting happens here, that when I multiply the input by 2, I get a horizontal shrink by a factor of 2, or it's scaled by 1/2. And hopefully at this point you'll believe me when I say that my inputs that will be my determining and defining inputs for my new graph for g of x equals f of 2 minus x are negative 2, 0, 2. But let's walk through it. So g of x is the square root of 1 minus 1/2 x squared. If I plug in negative 2 in for x, when I multiply that by 1/2, I get negative 1. I square that, I get 1. 1 minus 1 is 0. When I plug in 0 for x, I get the same thing as I did before, because when I multiply by 1/2, I get 0. I square it, I get 0. 1 minus 0 is 1. And then if I plug in 2 for x, 1/2 times 2 is 1. I square it, I get 1. I get 0. When I subtract that from 1. And then take the square root. So my new coordinates are negative 2, 0, 0, 1, and 2, 0. And that would be my daughter yelling if you heard that on the video. I apologize. So here is my graph of f of 1/2 x, and my transform function has been horizontally stretched away from the y-axis. My horizontal shrink by 1/2 was towards the y-axis. And again, both of these transformations affect the inputs, and so these are horizontal transformations. One of the key things to notice that when you had vertical dilations, when you multiplied by 2, then you stretched away from the x-axis. But for the horizontal, when you multiply your input by 2, you shrink it towards the y-axis. Conversely, when you multiplied by 1/2, then you did a shrink towards the x-axis. Now when you multiply your input by 1/2, you get a dilation away from the y-axis. So that's just good to realize. It kind of does the opposite of what it did for the vertical transformations when it's a horizontal transformation. Last, I want to make sure we understand reflections. So here we are going to see negative f of x. When x is negative 1, well, first of all, let's write down what g of x is. So g of x is the negative square root of 1 minus x squared. When x is negative 1, I plug that in. I'm going to get 0 under the square root. The negative of 0 is still 0. When x is 0, I'm going to get a 1 under the square root, but then the negative of that square root of 1 is going to be negative 1. And then when x is 1, I get a 0 under the square root. Negative of 0 is still 0. So notice my new points are -1, 0, 0, -1, and 1, 0. So I get the same graph. It's reflected over the x-axis. On the other hand, when I'm looking at g of x is the square root of 1 minus -x quantity squared, then when I plug in -1, I still get 0. When I plug in 0, I get 1. When I plug in 1, I still get 0. In this case, I get the exact same graph. What you don't see is that this has actually been reflected over the y-axis. So if this graph hadn't been symmetric over the y-axis, then you would have seen something change. So, for example, if I had started with this graph, and this was f of x, then g of x, looking like f of -x, would then look like this graph. So it's a reflection over the y-axis. And so those are our two reflections. Once again, you can see that this reflection affects the outputs. So it's a vertical transformation. This reflection affects the inputs. So it's a horizontal transformation. And you can kind of see or think of those reflections as vertical and horizontal. So we have covered now shifts. We can do vertical shifts up and down. We can do horizontal shifts left and right. We have talked about vertical stretches and shrinks away from the x-axis, and then horizontal stretches and shrinks towards the y-axis, reflections over the x-axis, reflections over the y-axis. We're going to kind of put it all together in one example. So when I'm looking at transformation of functions, I want to work inside to out. And that's just because we always do this stuff in parentheses first when we're doing order of operations in math. So I want to work my way inside out to follow my transformations. So the first thing I notice is that inside I have a horizontal shift, and I have to remember that the plus, does that move me right or left? So I have a horizontal shift, and hopefully you are able to answer that it was left by 1. So if I just graphed f of x plus 1, what I would see is my whole graph shifted left by 1. Next, I have that 3 times f of x plus 1. So that's a dilation, and it's on the output, so that's a vertical stretch or dilation, and it triples those outputs. So I can then multiply all of my outputs by 3. The output of 0 stays at 0, but the output of 1 now goes to 3. So my new graph will look like this. Notice I'm keeping these 3 reference points so I can track where they went. And this output here would have tripled if I had wanted to track a different output. And then last, now that I've done my horizontal shift and my vertical stretch, I have the -2, which hopefully you recognize that as a vertical shift down by 2. So I'm going to take each of these points and move them down 2. And now my new graph looks like this. And that's more than one transformation at a time. I hope this summary helped.